you have 50 centimeters of wire, and you have to use part of this wire to make a rectangle that's twice as long as it is wide, and the rest of the wire, if there is any left, to make a square. What should the dimensions of those two shapes be, the rectangle and the square, if you want the total area to be as small as possible? So we're going to try to minimize area. And then there's a second question in here that we'll come back to later. What if you want the total area to be as large as possible? Okay, so step one is draw a picture. If there's a picture to be drawn, that's what you should always do first. So I have to make a rectangle that is twice as long as it is wide. So something like this. So the width would be x and the length would be 2x. And then also a square. So the two sides are the same, y and y. Okay, so when you're going through the steps for any optimization problem, you typically, after you draw a picture and define some variables, is you try to come up with two equations. So let's see, they told me that I have 50 centimeters of wire. So these 8 line segments I drew, 1, 2, 3, 4, 5, 6, 7, 8. When I add up all of those lengths, I have to get 50. Okay, so with my rectangle, x plus 2x plus x plus 2x, that's 6x. And then my square, it has a perimeter of 4y. And when I add those together, I have to get the 50 centimeters of wire that I used to build those two shapes. And then my other equation is going to be area, because that's what they're asking me to minimize. They want the total area of the two shapes to be as small as possible. So the area of the rectangle is 2x squared, and the area of the square is y squared, and we'll call that A for area. And that's what I want to minimize. Okay, which means that A needs to be a function of just one variable, and hopefully I'll have a quadratic and just need to find its vertex. So I have two variables. That is not helpful. I need this to have just one variable. So that's where the other equation comes in. I'm going to solve for one of the variables over here and plug it in over here. So I'm going to solve for the y over here. So I'm going to subtract 6x from both sides, and I get 4y equals 50 minus 6x, divide by 4, and I get y equals, now I can do the 4 into both terms. 50 over 4 is 12 and a half. And 6 over 4 is 1 and a half. So y is 12 and a half minus 1 and a half x, and I'm going to plug that in right here. Instead of y, I'm going to put this expression with x's in it. So I've got area equals 2x squared plus, instead of y, I have 12.5 minus 1.5x squared. Now I have area as a function of one variable, just x's. I just have to simplify this and find its minimum. So I'm just going to rewrite this formula. So I have 2x squared plus 12 and a half minus 1 and a half x squared means 12.5 minus 1.5x times 12.5 minus 1.5x. And then I have to FOIL these two binomials to multiply them together. So I get area is 2x squared plus 12.5 times 12.5 is 156.25. And then the outer and the inner, those combine to negative 37.5x. And then the lasts come out to 2.25x squared. So I combine like terms, and I have area equals 4.25 x squared minus 37.5x plus 156.25. So that is a quadratic that opens up. It's quadratic because of this squared right here. It opens up because the leading coefficient is positive. So it's a quadratic that opens up, which means its vertex is a minimum. So again, I'm going to draw a very rough sketch of this parabola. X is representing a length, so it's going to be some kind of positive number. And that's my horizontal axis. And then my vertical axis is area. Again, that's going to be some positive number. So I've got a parabola that opens up like that. And this vertex, h comma k, the h is x, the length of my one side of my rectangle, and the vertical axis is area, so k is an area. They didn't ask me what the smallest possible area is. They just said what dimensions should the shapes have. So really, I'm looking for the lengths x, 2x, and y. That's the answer to the question. So maybe I'll highlight those to remind us. We need to find these dimensions, and that will answer the question. So h is x, right? So h is the smallest x value on this parabola. So that is what I'm looking for. H is the x coordinate of the smallest y value on this parabola. So h is what I'm looking for. Okay, so h is negative b over 2a. That's 37.5 over 2 times 4.25. And you get approximately 4.41. Okay, so that means that x is 4.41, 2x would be 8.82, and then y I can calculate using this formula, right? I have an equation that tells me y. So y is 12.5 minus 1.5 times 4.41, and that gives me about 5.885. So those are the answers to minimizing the area of those two shapes. To find the maximum possible area that we could make out of the two shapes using 50 centimeters of wire, I'm going to look at this graph again a little more carefully. The graph of the parabola where area was 4.25 x squared minus 37.5x plus 156.25. Okay, so I know this is a parabola that opens up. I know that its minimum happens when x is 4.41. Okay, so 1, 2, 3, 4, almost 4.5. And then the y value at that point, I do not know yet, but I'm just going to throw it on there. Okay, and I know the x coordinate of this point is 4.41. The y coordinate I could figure out by plugging 4.41 into the function. So let's do that so that I can graph this as carefully as possible. So area would be 4.25 times 4.41 squared minus 37.5 times 4.41 plus 156.25, and that comes out to approximately 73.5. So that is the y coordinate of the vertex of this parabola that opens up. the y-intercept is 156.25, because if you make the x's 0, you get 156.25. Okay, so I'm going to draw this parabola that opens up like that. Like that. That's 156.25. 0, comma. Okay. So we have the minimum. We have the minimum point right here. The question now is, what is the maximum? And if we were doing this problem out of context, we would say, well, this graph goes up forever to the left and to the right. The y values just keep getting bigger, so we would say there is no maximum. But when we think about the context, remember that the x-axis represents x, which was the length of our rectangle, one side length of our rectangle. And then the y-axis was area. So just to remind ourselves what x was, I'm going to draw the picture again. We had x and 2x, and then a square of y and y. And I want to think about the numbers that make sense for x. So x has some natural limits on it. The first one being that it can't be negative because x represents a length. So x can't be negative, which means that there is a bound right here. Okay? So I can't, x is bounded by 0. Can't be negative. Is there a biggest number that x can be? So the biggest number x could be where I make a rectangle that is twice as long as it is wide. I don't have to make a square. They said only make the square if you have wire left over. So we're not going to use any wire in the square so that I can make x as big as possible. So I want to use all my wire to make a rectangle with these limitations, x by 2x, which means that 6x, the perimeter of my rectangle, would be 50, all 50 centimeters of wire. Divide by 6, and I get x is 8.33. So that's the largest that x can be. So I'm going to put a little mark on my x-axis at 8.33. 3, 4, 5, 6, 7, 8, a little bit after 8. Okay, like that.